they won't let me. So, also, fun fact, when they knocked down the old building, I was saying, hey, those buildings have blinds. Can I have blinds? And they're like, no. I was like, can we just use those blinds? And they said, okay. So we're like, okay, that's the plan. We're going to save those blinds, we're going to cut them to fit, and we're going to install them in the science building. And that's not what happened. At some point, the building got knocked down, and I said, did you get the blinds? And they said, no. Why would we want to do that?
Memory we talked about this.
Yeah. Oh well. So yeah, and one of these days I'm just gonna be like, you know what? I don't care. I'm gonna put something up there. You know, I'm gonna build something. And
Just puts tinfoil up.
Yeah, not even supposed to do that anymore.
Tinfoil hats.
Yeah, but anyway.
I think we should make
That tinfoil's been up there for like 10 years, 15 years.
For the car shade.
Yeah.
Why don't we all cut it in half?
I have no clue.
Stick it
Yeah,
That's actually not a bad idea. I'll probably come up with something like that. But anyway, okay, so enough talk about what doesn't work. So vectors. Vectors are things, variables that have a direction and a magnitude. Okay? A direction and a magnitude. So previously we've been talking about velocity, and we say we have positive velocity or negative velocity, or positive velocity or negative velocity, or negative displacement or positive displacement. So when a variable also needs a direction, it's a vector. Okay? When you look at your speedometer, the speed it gives you is not a vector, it's a scalar. If you want to turn a scalar into a vector, you also need a direction. So you look at your speedometer and it says 65 miles per hour, that's a scalar. If you also have a compass and it says 65 miles per hour due east, that's a vector. Make sense?
So, like ships and stuff, they have vector measurement.
Yes, you gotta move with vectors. So a vector it basically has a direction and a magnitude. Question?
So does scalar just have magnitude?
Yep, scalar just has a magnitude, exactly. Have you guys learned polar coordinates in math yet?
Okay.
So a polar coordinate, if you haven't learned it, you will soon. A polar coordinate is something that is given by its magnitude and its angle to the origin. Okay. So you will learn vectors, they call it polar coordinates. It's usually graphed on a circle instead of a Cartesian rectangle. So a vector has both magnitude and direction. So magnitude, how long the arrow is, direction, the angle from the origin. Make sense? Now, how you convert between Cartesian coordinates, or the x and y, you have x and y. How you convert between those and polar coordinates is with trig functions, which we're going to talk about. Now, since a vector only has magnitude and direction, you can translate it all over the page without changing the vector. Okay? So this vector can be translated anywhere on the page. It doesn't change the vector because it doesn't change its magnitude or its direction. If you rotate a vector, that changes it. If you lengthen or shorten a vector, that changes it. But moving it around the page does not change it. Cool? Now the reason we're actually going to be using vectors is because eventually we're going to transition from one-dimensional motion, up, down, left, and right, to two-dimensional motion, firing at angles. That's where we're going. So you've all done one-dimensional vector addition. When have you done one-dimensional vector addition? Where you add vectors together. You did it in elementary school. You did it in like 2nd or 3rd grade. Remember number lines?
Okay.
Yeah, remember number lines? Where you had a line and it had arrows and then there was a 0 right here and you had tick marks. You're like 4, and then you had another one and it was like -4. So you were like, if this arrow is added to this arrow, what's the result? And you said 0 because that was one-dimensional vector addition. They were doing one-dimensional vector addition way back in 2nd grade. So if this vector is added to this vector, the result is this vector. And how do you get that? This is called the graphical method of vector addition. You add vectors head to toe, from the head of the first vector to the toe of the second vector. You add vectors head to toe. So you take this vector and you move it up here, And what you're left with is a resultant that starts, so we're going to translate this vector up here, and what we're left with is a vector that starts here and ends here. Wow. There. Okay, so that's vector addition. You just take the first vector and you add it to the second vector. Make sense so far? All right. So here's another one. What would happen if you added this vector to that vector? The result would be that vector. So you just take this vector, translate it over. You translate this vector over and you translate it like that, then the resultant is where you started to where you ended, which is this vector right here. Which by coincidence just happens to be green, because blue plus yellow equals green. Okay.
Lights, yay.
Make sense? Okay, give me a thumbs up if this makes sense to you. And we're moving on. Two-dimensional vectors, this is why we're here. We're here for two-dimensional vectors. Two-dimensional vectors are vectors that do not follow the x and y directions. They're not all x or all y, they follow both of them. So you can still add them quantitative or qualitatively head to tail. So if you wanted to add that vector to that vector, that's the resultant vector. I'll show you again. So imagine you got two vectors, that vector and that vector, and you just take them and you move them head to tail, and the resultant vector starts where you started and ends where you ended.
Oh,
make sense?
Shoot.
Now there is a temptation to go head to head or tail to tail. Don't do that. Take vectors, go head to tail. Now, does it matter what order you use? So the big vector is the first vector and the little vector is the second vector. Would it matter if you went little vector to big vector?
Yes.
No, it wouldn't, because addition is commutative. Okay, so it doesn't matter. So 7 plus 5 is the same as 5 plus 7. Similarly, when you add vectors, it doesn't matter what order you add them. In fact, if you kind of look, imagine this vector translated up here. It's going to give you another green vector. It's just going to be somewhere else on the page. Does it matter that it's somewhere else on the page? No. Because, again, vectors only have two values. They have magnitude and direction. Where they are located doesn't matter. Does this idea make sense? All right. Gesundheit. Give me a thumbs up if you're with me so far. Okay. Wave your hand around if you have a question. All right. And those viewing at home, like and subscribe, get the bell on. So here's two vectors. So now they're both pointing in a negative y direction. So both vectors have a negative y component, and this vector has a x component that is positive. This vector has an x component that is negative, and it turns out that the y's add up and the negatives cancel out. We'll see that again. So here you got, there we go. There's a vector pointing in negative y, there's a vector pointing in negative y. Put them head to tail, and the resultant vector is that. You ready to practice on your own?
Yes.
Oh yeah.
Oh yeah, let's do this. Okay. So here is, oops, there we go. Okay, so if you wouldn't mind, take those two vectors as best you can, sketch them, and see if you can figure out where the resultant vector is going to go. And when you're done, show your neighbor and see if your art agrees with her art.
But if they don't associate identify as a bird.
See if its art agrees with their art.
I think he's talking about me being the guy.
Oh yeah.
Remember to police your crumbs, don't feed the ants.
Yeah,
Okay, so you got one vector pointing in the positive x, or a little bit positive x, a lot positive y. One vector pointing in the negative y and a little bit negative x. So you would hope that they would cancel out a little bit. So if you put them together, that vector plus that vector gets you that vector.
Sweet.
Okay. Does that look kind of like what your resolved vector is? Now, once again, does it matter the order?
No.
No. You could have done this one plus this one, so you could have like put this one right here, and it still would have drawn the same vector. You could have like moved that one over here, it's right here, it still would have drawn the same vector. Okay. How about one more? So now we got two vectors pointing in the very y. One's got a positive x, one's got a negative x. What's the resultant going to look like? One is very, very big y, one is a little bit positive x, the other one is very positive y, the other one is a little bit negative x. So I take it from the chat, are you ready to move on?
Oh yeah.
You get something that looks kind of like that plus that gives you mostly verticalish?
Yes.
Cool. Now give me the thumbs up if you're with me. Okay. If you have questions, wave your hand around in the air. No, Mr. Byers, stop. Listen.
Okay, quick question. Why does the, like, it being positive or negative matter again? How does it cancel each other out?
Head.
Yeah, imagine, yeah, because you're going to go head to toe. So if this one is positive, this is positive, you're going to have some positive y and positive y added together. If this one has some negative component, this one has some negative component of x, this one has some positive component of x, they're going to kind of cancel each other out. And that's the next thing we're going. Now that we've done graphical addition, we're going to break these things into their components, which are their x component and their y component, and add those together. And that's where the real value is. This is called qualitative addition. Do you know what qualitative means?
It's high quality.
Okay, so a qualitative description would be like, Rome is tall.
Oh shoot, you don't
Okay,
know.
Daryl is smart. Okay,
Oh.
those are things that don't have numbers attached to them. But if you want to make something quantitative, quantitative values tend to be more precise and more useful. It'd be like, Trump is dumb. That's like, well, okay, we know he's dumb, but how dumb? I mean, they're like, Trump has an IQ of pi. You know, so, something. Yeah, he has a negative IQ. He's bigly dumb. So anyway, so now, you don't need to write this down, but it's actually kind of cool. Vector addition is not limited to only two vectors. You can put a whole bunch of vectors in. So take a look, this is actually kind of fun. If you add that vector to that vector, to that vector, to that vector,
Ooh.
can you guess the resulting vector just by looking at it? Well, look at this. Does it make sense that that vector moved over here is going to produce a vector that looks like that? So this vector plus this vector would equal this vector? So this vector put here, we create a vector here, which would cancel this one out, and the resultant is that vector.
Yo.
So that vector
Quick
plus
math.
that vector, and it doesn't matter what order you go, plus this vector, gets you a vector that looks just like that one. Because if you take this vector and move it head to toe over here, the resulting vector is going to be a diagonal line right here that's going to cancel out this vector, leaving this one left. Isn't that fun?
That's cool.
All right. So now we're going to resolve vectors into their components. By resolving vectors into their components, we find the x value. Did you not need to test?
I didn't have an account, so they just sent me back.
Oh, okay. Welcome back. So by resolving vectors into their components, we find their xness and their yness. We find a vector's x component and their y component. And we do that, of course, with triangle math. Some people call triangle math trigonometry, triangle measurement, but we're going to call it trigonometry. So there's a vector, very simple vector. It has x component, it has y component, and it has an angle. So what resolving vectors into their components does is it tells us this is how much xness this vector has, this is how much yness this vector has. Now, how might we go about figuring out how much xness this vector has?
The other side's length.
Well, what we have is a magnitude and an angle. We have a magnitude and an angle. So to find out the xness of a vector, we use triangle math. We want to know what this leg is. So the magnitude is the hypotenuse, and we use the hypotenuse and the angle to find the leg. Remember our triangle math? So if this is hypotenuse, which it is, and this is opposite, sinister, which it is, and this is adjacent, or adjective, which it is, then if you wanted to figure out x, you'd be like, all right, remember trigonometry, angle measurement?
It would be tangent.
Equal.
Tangent is adjacent over hypotenuse, which you don't have. All we have is magnitude and angle. It's cosine, yeah. So remember that cosine of an angle,
Is adjacent over hypotenuse.
correct. So, is that blue? Yeah, okay. So cosine of an angle is adjacent over hypotenuse.
So you have cosine.
Yeah. So you can basically say cosine angle equals adjacent leg, which is, in this case, x. So equals x over the magnitude m. Make sense?
And cosine theta.
And if you want to get m by itself, it's just x equals m cosine theta. Chris?
So in this situation, we only have the magnitude, and we're trying to find the x-axis.
Okay. Yeah. You're trying to find how much of that vector is xness, the xness of that vector. So by resolving things into their components, you're saying, all right, this vector has this value in x, and then it has this value in y. This is how you convert from what you're going to learn as polar coordinates to what you're going to learn as Cartesian coordinates. Okay. Does this idea make sense so far? We're going to do this in simulations too. We're going to practice it today, practice it tomorrow, do it in simulations later on this week. So if the x of the vector is m cosine theta, what do you think the y is?
The y. Is it all inverse cosine?
So the y, where's my green? So
That's funny, that was a P reference.
if sine of an angle is the opposite over the hypotenuse, which is therefore the y over the magnitude, so if the sine of the angle is y over the magnitude, would it make sense that y is magnitude sine theta? Can you follow that math from here to here? So if you want the y-ness of a vector, then it's m sine theta. You want to know the y-ness of the vector is m sine theta.
It's the same length as the y.
It is the y-ness of the vector. So it is, if you broke this vector into components, it's going to be how much y it has. It's kind of like this. If you had a helicopter, you could go from Phoenix, Arizona to Denver, Colorado. Or you could go from Phoenix, Arizona to Houston, then up to Denver. You're going to get to the same place. I don't know if that's geographically correct, but I'm just guessing here. But does that make sense? So, all right, so this is what happens. The quarterback takes the ball, and he runs 10 yards to the right. Then he throws 10 yards forward and the receiver had just ran a diagonal post pattern and caught the ball. They both ended at the same place.
We ran an arrow route.
Yeah, an arrow route. Do it like a vector. Okay, coach, I got it. Okay, 38. I need you to go 6 meters at 24 degrees. Number 85. I need you to go 8 meters at 10 degrees. What do I do? You go long.
You're teaching us all the secrets of Nick Saban's offense.
Yeah, it's all geometry. Okay, does this idea make sense? So why is this important? It's important because you can take the components and then you can add them, add the x component to the x component of one vector to another vector. Add the y component of one vector to the y component of another vector. Why do you have to do this? Because the single most important concept in all of two-dimensional motion is that motion in the x and motion in the y are what of each other? Independent. They are independent of each other. So if I throw this ball at Corey, gravity acts in what direction? In the y direction. And if he throws it back at me, does gravity say, oh, I didn't realize you were moving the x. Continue on. I won't touch you. No. As far as gravity is concerned, all the ball is doing is this. That's what gravity's thinking is happening. But I know that I also gave it some x velocity. Okay? So x motion and y motion are independent of each other. Does that make sense? So when we have vectors, now I threw it, I did not throw it exactly horizontally because I knew it wasn't going to make it, it would just hit Adam in the face. So I had to throw it with an upward trajectory too. That's where we're going. We're basically talking about projectiles. How I threw it at a diagonal direction, and there was motion in the x direction and motion in the y direction. Questions? Are you ready to practice with some vectors? This is probably going to take us to the end of the class.
Yeah.
All right, you're going to blow away your pre-calculus teacher when you get to polar coordinates. You'll be like, I already know how to do this. We did this in physics. And you'll be like, okay, continue on. You may play your fork now.
Batteries teach us a different way to do it.
Oh,
Probably not.
What is with this?
And then he'll bring up the metric system.
Or-
thing.
It'll be like 32 feet per second. Darn it. Okay. So break these vectors into components. You got component one, or vector one, that has a magnitude of 10 degrees and a angle of magnitude of 10 units and an angle of 15 degrees. Vector two has a magnitude of 6 units.